Here on this section we have continuity definitions. Let C be a real number that is either an interior point or an endpoint of an interval in the domain of f. The function f is continuous at Cf. Limit of f of x as x approaches c is equal to f of c. The function f is right continuous at c, or continuous from the right, if limit of f of x as x approaches c from the right is equal to f of c, and the function f is left continuous at c, or continuous from the left, if limit of f of x as x approaches c from the left is equal to f of c. Here we have this graph for this function f of x. What we have here on left side is continuous from the right. Here is continuous from the left. And here is continuous from both sides. So it's from the left and from the right. That's why it is called two-sided continuity. Now here on this part we have continuity test. The function f of x is continuous at a point x equal to c if and only if it meets the following three conditions. So what we have to do first is finding f of c, see if this value exists, and then find limit of f of x as x approaches c. And finally compare these two, number 1 and 2, and see if f of c is equal to limit of f of x. If was equal to, in that case, we're going to say our function is continuous at a point x equal to c. Now here we have this example. The following function is continuous over its domain. So domain starting from left to right, here we have -2 up to this point, +2. So domain is bracket -2, comma, +2, close bracket. It is right continuous at x equal to -2. So it is right continuous at x equal to -2, and it is left continuous at x equal to +2. So here what I did on this part, finding limit of our function as x approaches -2 from right, that is equal to square root of 4 minus, using -2 for x here on this part, and then using second power, that is equal to square root of 4 minus 4, so it's square root of 0, and the answer is 0 for this part. And also finding function value when x is -2. So f of -2, that is square root of 4 minus -2 squared. So here in this case, again, we have 0. And now, finally, comparing these two that we have here, we see that we have same answer. So that means limit of what we have here. So what I used, here we have y equal to square root of 4 minus x squared. So I used y is f of x. So let y equal to f of x. This means I have limit of f of x as x approaches -2 from the right. That is equal to f of -2. So it's equal to our function value. And also what I did here on this part, finding limit of f of x, or limit of square root of 4 minus x squared as x approaches 2 from the left. So that is equal to square root of 4 minus, instead of x, I used 2. So 4 minus 2 squared, that is equal to square root of 0, and the answer is 0 on this part. And then finding function value when x is equal to 2. So f of 2 is equal to square root of 4 minus 2 squared. Again, here the answer is 0. So comparing these two, what we have here, we have is same answer. That means we have this conclusion. So limit of f of x as x approaches 2 from the left, that is equal to our function value when x is 2. Based on what we did on this part, our conclusion is that our function is continuous over its domain -2, +2. Now here on this part, the greatest integer function is continuous at every real number other than the integers. It is right continuous, but not left continuous at every integer point. For example, limit of our function as x approaches 1 from right is equal to 1. And also we have same answer for function value that is equal to 1. So f of x when x is equal to 1, that is equal to 1. But for left continuous, as x approaches 1, from left, we have this point for our limit, but for function value, we have this point. So limit of f of x as x approaches 1 from the left, that is what we have here on this part, that is 0. But for function value for f of x when x is 1, that is based on this point, and it's equal to 1. So this means we have right continuous, but we don't have left continuous in this case. Now what we have here on this part, our function is equal to 1 over x. Because of having denominator, this denominator shouldn't be equal to 0. So that means in this case, x is not equal to 0. So this function is continuous for all x in its domain except for x equal to 0. So it is not defined at the origin. So it is not continuous on any interval containing x equal to 0. Properties of continuous functions. If the functions f and g are continuous at x equal to c, then the following algebraic combinations are continuous at x equal to c. Number 1, here we have sums. So this is the sum of these two functions, f and g. Then we have differences of these two functions. We have constant multiply, so it's k times f, and that is for any number k. Product of two functions, quotients of two functions. But here in this case, we have denominator, so our denominator is not equal to 0. So it is not defined when denominator is 0. Powers or function to the n power, n is a positive integer. Roots. Here we have nth root of our function. So provided it is defined on an interval containing c, where n is a positive integer. Now here on this part we have compositions of continuous functions. If f is continuous at c and g is continuous at f of c, then the composition of these two functions is continuous at c. So what we have here, this is based on theorem 9. So this function is continuous at c. So if I use, for example, our function f of x, instead of x using c, we have f of c. And then g of x is continuous at f of c, meaning that instead of x we used f of c, so we have g of f of c. And also here what we have here on top is g of f. So g of fx, instead of x, if I use c, that means composition of these two functions continues at c. So again, we're going to have this part, g of fc. Determine the point at which the given function f of x is continuous. Here we have the differences of two functions. Let g of x equal to 12 divided by x minus 13 and h of x equal to 5 times x. Thus, h of x, that is the product of a constant function and the identity function, and both of these are continuous over negative infinite, positive infinite. But g of x is continuous on negative infinite, positive infinite, except at what we have in denominator is x minus 13, so that shouldn't be equal to 0. So it's except x equal to 13. So the point is that we have to see where our function is not defined. So in this case, we have denominator. So denominator equal to 0, and the answer for x is equal to 13. This means g of x, this function, is undefined at this point. So we're not going to use that point. Here on this part it says it's continuous over negative infinite, positive infinite, except x equal to 13. This means f of x is continuous on negative infinite, positive infinite, except at x equal to 13. So our interval notation is we have negative infinite, positive infinite, except 13. So it's negative infinite, comma, 13. Use parentheses, union, open parentheses, 13, comma, positive infinite. At what point is the following function continuous? So here in this case, we have numerator divided by denominator. For example, I'm going to use p of x for what I have in numerator and q of x for what I have in denominator. And both of these are continuous for all x. And what is given is quotient of these two polynomials. So it's p of x divided by q of x. And that is equal to factor what we have in denominator So this function is continuous for all x except what we have in denominator. So in this case, we have x minus 7 times x minus 4. This means our function is continuous for all x in its domain except for 7 and 4. So writing our interval notation. So the function is continuous at a set of x values. What we have here is parentheses, negative infinite, comma, 4, close parentheses, union, 4, comma, 7, union, parentheses, 7, comma, infinite, close parentheses. So this is our final answer for this part. And this was because our function is undefined for x equal to 7 and x equal to 4. Determine the points at which the given function f of x is continuous. We have square root of 9x plus 36. First, we have to find domain of our function. For square root of 9x plus 36 to be defined, we should have what we have inside the square root. That part should be greater than or equal to 0. So what we have here, 9x plus 36, that should be greater than or equal to 0. Now solving for x, subtract 36 from both sides. So this is 9x greater than or equal to negative 36. Divide by 9 on both sides. So what we have is x greater than or equal to negative 4. So this means our function square root of 9x plus 36 is defined on negative 4, positive infinite. So in interval notation, our function is continuous at the set of x values. And here is our interval. It's bracket negative 4, comma, positive infinite. So here is our final answer. At what point is the following function continuous? What is given, this function is a piecewise defined function. So what is given here on this part, the expression for x not equal to 3, that part is rational expression. But for x equal to 7, what is given is a constant. So here we have division of two polynomials. That means this part is not continuous at x equal to 3, because here in the denominator we have x minus 3, and finding what we have for x in the denominator, x is equal to 3, and that shouldn't be equal to 3, because in that case this part will be undefined. This means this rational expression is not continuous at x equal to 3, as it is not defined at x equal to 3. But for when x is equal to 3, our function is equal to 5, based on what we have here on this part. So at this point, x equal to 3, f of x is defined to be 5. Now we want to find limit of x squared minus x minus 6 divided by x minus 3 as x approaches 3, and compare that one with our function value when x is equal to 3. So our limit so here I factor what we had in numerator. And now simplify, we have limit of x plus 2 as x approaches 3. So 3 plus 2, and here the answer is 5. And what we have based on what is given on this part, f of 3 is equal to 5. That means our limit as x approaches 3 for this function, that is equal to our function value when x is equal to 3. Because of this conclusion, our function f of x that is continuous at x equal to 3. Limit of continuous function f limit of f of x as x approaches c equal to b, and g is continuous at the point b, then limit of g of fx as x approaches c is equal to g of b. Example, we want to apply this theorem here on this part. So limit of cosine, here inside we have 2x plus sine 3 pi over 2 plus x, and here in this case x approaches pi over 2. So this is equal to cosine. We want to find limit of each one of these. So limit of 2x as x approaches pi over 2 plus limit of sine 3 pi over 2 plus x. And here x approaches pi over 2. So this is equal to cosine. Here, instead of x using pi over 2, we have 2 times pi over 2, and that is pi. So this is for the first part, plus. Now here again, for x, we have pi over 2. So we're going to have sine 3 pi over 2 plus pi over 2. So that is cosine pi plus sine. We have 4 pi divided by 2, and that is 2 pi. Sine 2 pi is 0. So our final answer is based on cosine pi. And cosine pi is equal to -1. So this is final answer for this part. Team 11, the intermediate value theorem for continuous functions. If our function is continuous on a closed interval a, b, and if y naught is any value between f of a and f of b, then y naught is equal to f of c for some c in this interval a, b. And here we have, on the x-axis, we have this interval a, b. And this point c is in this interval a and b. This y naught is in this interval f of a and f of b. So if we use x equal to c, and our function f of x, we're going to have f of c, and f of c is equal to y naught. So for when x is equal to c, f of x is equal to f of c. In this case, we used y naught for f of c on y-axis. Use the intermediate value theorem to prove the equation has a solution. Then use a graphing calculator or computer grapher to solve the equation. So here we have 7 sine x equal to x. We can write this equation as 7 sine x minus x equal to 0. Let f of x equal to 7 sine x minus x. Now choose x values a and b such that 0 is in the interval f of a, f of b. So we can use x equal to negative pi and x equal to pi to prove that our equation has a solution based on what we have in this theorem, intermediate value theorem. So substitute negative pi into f of x. And here in this case, f of x is 7 sine x minus x. So f of negative pi, 7 sine negative pi minus negative pi. So here is 7 sine negative pi, that is 0, and what's left here is negative times negative pi, so the answer is positive pi. And now substitute pi into f of x. So we have 7 sine pi minus pi. Simplify, our answer is negative pi, because here 7 sine pi is 0. So the answer is negative pi. Since f of negative pi is positive and f of pi is negative, our function equal to 0 for some x in the interval negative pi and positive pi. Now here I'm using graphing calculator. So we have x and we have y equal to 7 sine x and what was given was 7 sine x equal to x. So here the straight line is for y equal to x and blue part is for y equal to 7 sine x. And the third part I try to find the intersection between these two. So what was given was 7 sine x equal to x. and these green lines as to find intersection points. So we can zoom in. Running to 4 decimal place, the answer for this part is -2.7395. Here we have 0, and the third one is positive. Running to the closest number we can have to this line is, if we run to 4 decimal place, it's 2.7395. So these are the 3 points that we have in intersection. So this is 1, 2, and 3, these 3 points. So here they rounded to 3 decimal place. But if was asking to round to 4 decimal place, we can zoom in and find what exactly our answer is. So using graphing calculator, we solve the equation and our answers rounding to 4 decimal places, -2.7395 and 0 and +2.7395.